easy way to look at it. So parts per million and parts per billion is how you measure very small amounts. So if you think of a percent solution is really like a part per 100. Okay, because you put it in grams per mil and you multiply your answer times 100, and that's how you put it in the percent form. Parts per million and parts per billion, you're going to do exactly the same thing. So you're going to put your answer in grams per milliliter, grams of solute divided by milliliters of the solution, and for parts per million, you multiply it times a million. Parts per billion, you're going to multiply it times a billion. Okay, so go and set it up the same as you would for a percent solution in order to solve for this. So I think the first one we did, that was actually not what I did. So in this one, the copper one, so copper in drinking water, it's toxic if it's greater than 1.3 parts per million. So if we have 150 milligrams of copper in 100 milliliters of water, is this toxic, yes or no? So first thing to do, you always want to put it in put units in grams per milliliter. So 150 milligrams, you're going to have to convert that one to grams. 100 milliliters you can use because 100 milliliters, that's the volume that you want. So to convert 150 milligrams to grams, it's just a single unit conversion. Remember that the unit you start with, you always put in the bottom. So milligrams will go on the bottom, so it'll cancel. The grams is what you want to go to, so that goes on top. Whenever you see milli, what goes in front of it? 1,000. And grams is the base unit, gets a 1. It takes 1,000 milli to make one base unit. That is that unit conversion. So 150 divided by 1,000. It's 0.15 grams. So now we know grams and we have mils. We don't have to do anything with mils. So 0.15 grams divided by 100 milliliters. And since we want to know parts per million, what are we going to do with our answer? Multiply it times a million. So just make sure you put your units, set them up into grams per mil. I think last time I told you grams per liter. It's grams per mil.
Oh, we did it right last time.
We did? I just wanted to double check. That's why I went back and actually redid this slide. I was trying to make it so it looked a little simpler. Maybe, I was thinking.
I mean, that looks simpler the way you did it this time, but we did it right.
Okay, so in this, 0.15 divided by 100, and then times 1, 2, 3, 4, 5, 6. So I got 1,500 parts per million. So it's still really big. So is this toxic? Yes. Like a resounding yes? Like 1,000 times more than what you should actually have? Even though it's milligrams. Milligrams, remember 0.15 grams? Remember in lab balancing or weighing out grams? 0.15 is like just a couple of grains of salt. It's not very much, but in high concentration, it can have negative effects. So arsenic is the next one. Arsenic is toxic in levels 10 parts per billion or higher. So in this one, if you detect 0.08 milligrams of arsenic in a 7.5 liter water sample, is that toxic? So each time, just do the same thing. Figure out, take the mass of the solute, put it in grams. Put the solution volume in milliliters. Once you get that, you can divide them, then just multiply it times a billion to get your number. So we start off with 0.08 milligrams. So we're going to have to convert that one, just like we did the one above. Milligrams on the bottom, grams on top. So those units will cancel. So you're going to take 0.08 and divide it by 1,000. So it's going to get even smaller. So I got a decimal place with 4 zeros and then the 8. The volume is a 7.5 liter water sample, and I need to put that in milliliters. So in this one, what's my unit on the bottom in this one? Well, the unit you're given is always going to go on the bottom in the first unit conversion. And then the unit I want is milliliters. So milli gets the 1,000. So here, 1,000 is on top. Takes 1,000 millis to make a base unit, whether it's grams or liters. Liters and liters will cancel. So now 7.5 times 1,000 is 7,500. So now I have grams and I have milliliters. Divide them. 0.00008 grams divided by 7,500 milliliters. Whatever that is, I'm going to multiply times a 1 with 9 zeros. You get that's what I got. I got more 6s than that, but that's enough 6s. Okay, so in this one, is this toxic? Why? So I got 10.666667 parts per billion. Yeah, so anything over 10 is toxic. Okay, so toxic, the limit is 10 parts per billion. Anything greater than that would be considered toxic. Anything less would be considered safe. It's greater than 10. Okay, so this one's fluoride. So fluoride in drinking water is safely added up to 4 parts per million. So if your tap water has 0.62 milligrams of fluoride in 250 mils, is this considered safe? So anything over 4 parts per million, fluoride, the benefit of fluoride, and so fluorine, this is a fluoride salt. So fluoride is added to drinking water because it actually helps to make your enamel, the hardest covering, the hardest sort of component of the body, the covering on your teeth, it makes them more resistant to acid breakdown. So most of what you eat is either neutral or acidic. So when you have tomatoes, if you have coffee, if you have soda, all of those things are acidic in nature. And so those acids can slowly dissolve the cover on the teeth, the enamel. So that's why they add fluoride. So fluoride helps to like reharden it. It helps to keep it from breaking down. But if you have a lot of fluoride in your water, you can actually start to develop spots on your teeth. So you can actually start to develop fluoride deposits on the teeth, and you can also start to see that in bone as well. So that is why there's that limit as to what is safely added. So 4 parts per million. So we want to put this in what? What do we say? What's the unit value? Grams per milliliter. Okay, so check your units. The solute needs to be in grams. The volume of the liquid, the solution, needs to be in milliliters. So I have 0.62 milligrams. So I got to convert that one. Okay, so I'm going to have to go from milligrams to grams. Anytime that you see milli, put 1,000 in front. Grams gets the 1. So 0.62 divided by 1,000. Milligrams and milligrams will cancel. .00062 grams. Milliliters, do I have to do anything? No. So milliliters is fine. I can use that as is. And then since I want parts per million, you just multiply the answer times a million. 2.48. So would this level be considered safe?
Yes.
Yeah, because it's less than 4. Okay, so being under the limit, it wouldn't be toxic, it would be fine. So parts per million, percent solutions, there's a couple other ones. We'll do a few more of them. Molarity, okay? So whether you're talking about molarity, percent solutions, parts per million, parts per billion, the key thing is just knowing what those units mean and being able to like convert it back into a usable form. So this one says how many grams of glucose is in a 3-liter solution with a concentration of 0.65 molar glucose. So 0.65 molar, and I have a volume. So, and I want to know how many grams. So what does that big M mean? 0.65 M glucose means 0.65 what? Every time you see that big M, just change it back to what the unit is, because then you can use it. It's just an abbreviation. That capital M means moles per liter. So it's in a solution, 0.65 moles of glucose per liter of the solution. So if I know the concentration and the volume, I can figure out how much solute. Take the concentration in moles per liter, multiply it times the volume. See that liters and liters are the same, so you can use that. Liters and liters can cancel. You don't have to convert anything. So when you're using molar, this is going to tell you the number of moles of glucose. But I want to know grams. So I've got to do one more step. How many significant figures should this answer have? So 3.0 is 2 significant figures. 0.65 is 2 significant figures. So if I rounded this, what would it be? So I'd round this to 2.0. So the first part, take the concentration times the volume, and that'll tell you how much solute. If it's a percent solution, that's all you have to do. Okay? But if it's in molar, then remember you're going to have to figure out, work one more step and convert the number of moles to grams. And in order to do that, what are you going to use? That formula mass. So remember, the formula mass is the mass of each of the atoms in the formula. So glucose is C6H12O6. So there's 6 carbons. If you look, each carbon weighs 12. There's 12 hydrogens. Each one of them weighs 1. There is 6 oxygens, and each one of those weighs 16. So when I add all of those up, I get 180. So that's where the 180 comes from, the formula. That is the number of grams in 1 mole. It's called the formula mass. So the last part is just converting from moles using this value. What unit goes on the bottom? So moles goes on the bottom. Then the unit you're given is going to go on the bottom. Grams will go on the top. And there is 180 in 1. So you use the formula mass just like a unit conversion. Concentration times the volume is going to give you the amount of the solute. If you're talking about moles, you'll have to use the formula mass to convert to grams. So physiological saline is 0.9% sodium chloride. How would you make up 500 milliliters of this solution? So what do you see whenever you see percent? What can you change percent? You can change molar into moles per liter. When you see percent, that means what? So anything out of 100. So you know that it's going to be grams per 100 milliliter. That's a mass to volume ratio. Whenever you think in terms of percent, it's always how much out of 100. So 0.9% means 0.90 grams per 100 milliliters. So just like with molar, just convert the percent into what the number is, what that symbol means, and then that way you've got this to be able to use. So if I have 0.9 grams for every 100 milliliters of solution, and I want to make up 500 milliliters of the solution, how do I figure out how many grams? If you multiply it times the volume, what happens to milliliters? So the units will cancel. So it's 4.5 grams of sodium chloride. You would have to put that in a container and add enough water to make the volume what? What's the final volume? 500 milliliters. All right, so remember with this, you really don't know exactly how much water. You just know you're going to keep adding water until you have 500 milliliters and that salt's totally dissolved. But just like the last one, you take the concentration times the volume, and that'll tell you the amount of solute. Just like we did in the last one, if you look at the last one, same thing. Concentration times the volume tells you, this one tells you the moles of solute, but it's still telling you the amount of the solute. So they're both the same. take your, whatever the percent molarity, and just switch it to the number value so that you can use it. So the percent solutions can also be volume to volume. If your solute is a liquid and it's mixed into a solvent that's a liquid, you can have a volume to volume solution. The one above is sodium chloride. So sodium chloride's a solid. So that's where the gram amount would be mixed into a volume of the solution. So in this one, what is the percent alcohol in 750 ml bottle of wine that contains 112 milliliters of alcohol? So how do you figure out the percent solution? What is the volume of the solute?
112.
Mm-hmm. Mm-hmm. It's how much the solute is compared to the entire amount, multiply it times 100. So 112 mils divided by 750 mils times 100 is going to tell you your percent of ethanol or alcohol. Okay. So that's just the regular percent solutions. It's how much that smaller part is compared to the whole. So how much magnesium oxide would you need to make a 4% magnesium oxide solution in 650 mils? See if you can set that one up. Okay, so you change that 4% to 4 grams per 100 mils. Multiply it times the volume, so it's just the concentration times the volume. They're both in milliliters, so they'll both cancel. You don't have to do any kind of unit conversions with that. Milliliters and milliliters will cancel. 4 times 650 divided by 100 is? I got 2.6. What'd you get? 26? 26? Might have done something with my math. Well, that makes sense, because 4 per 100, and so 6.5 times. So 26 grams of the magnesium oxide plus enough water to make that 650 milliliter volume. If you have a solution with a higher concentration and you want to dilute it, you can do what's known as a dilution. So a dilution is just taking something with a known amount of solute and adding water so that the concentration is lower. So this is the example. I don't know if any of you have ever done this or ever seen this. This is how I had orange juice when I was a kid. Like, we never had orange juice bought out of a carton. We always got like the frozen cans. I have like, there's 4 kids in my family, so I don't know if that had anything to do with it. Plus we were all like, my one brother is 6'5", my other brother is 6'2", my sister's only 5'8", she's like short in my family. Okay, so this was a constant issue, is trying to keep food in the house, I think. So you can buy these like frozen orange juice concentrates. And so like my dad would leave it out overnight, so it would all be melted in the morning. And so he'd like pour it into a container, and then he'd add 3 cans of water. Just to be truthful, he would usually add 4 cans. So I never actually knew that orange juice like was really sweet until like I went and had orange juice at a restaurant. Because it was always really watery tasting to me, but it was so that it would like last longer. So the dilution was a lot more than what it was supposed to be. But do you see that the amount of orange juice in the can and the amount of orange juice at the end, it's still the orange juice. The amount of actual orange juice is the same. It's the amount of water that has changed. And so that has allowed it to be diluted. Well, you can do this calculation by increasing the amount of the solvent. We can change the concentration. And in fact, it looks a lot like Boyle's law. So you can calculate, if you know the initial concentration, if you know the initial volume, they are going to be proportional to any changes that you do in the volume and the effect of reducing the concentration. So it is oftentimes called C1 times V1, the concentration times the volume, will be equal to the change in concentration and the new volume. And just like we did with gas laws, you will always know 3 of the 4 numbers. So you'll either know the 2 concentrations in a volume, or you'll know the 2 volumes in 1 concentration, and you just have to solve for X type of thing, okay? You just have to rearrange the formula and then plug the numbers in. The only problems that you might run into is you do have to make sure your units are the same. So like if you had milliliters and liters, they need to be changed. But if you have 2% solutions, you can use those. If you had 2 molar concentrations, you could use those. As long as the concentration units are the same, it wouldn't matter which one you use. You don't have to convert those ones. So concentration, it could be molarity or it could be a percent solution. Either one of those are fine, but they need to be the same. And I won't give you them different. Just don't let them throw you. So if the concentration of a sugar solution is 100 grams per liter, and you dilute it to 20 grams per liter, in a final volume of 1.7 liters, how much of the initial concentration did you use? So in this, C1V1 is C2V2. So what is C1? So it's C1 is 100 grams per liter. So what is V1? What's the initial volume? That's what you're looking for. That's the unknown. That's the X. Okay? Because it says how much of the initial concentration. So what is the volume V1? So what's C2? And then what's V2? Okay? So just like we did with the gas laws, assign what each number is so that you figure out what your unknown is. Right now. Then the next thing to do, before you can plug it in, what do you want to do? Where are we going to move? What unit do we need to move? C1. We want to move C1. C1 is over on the left side in the denominator, so how do we move it? Divide both sides by C1. That will move C1 from the denominator to the opposite side and put it in the denominator. Right? So anything in the denominator can get moved to the opposite side as long as it's in the denominator or vice versa. So C1 down underneath. So now plug it in. So C2, 20 grams per liter, times V2, 1.7 liters, is divided by C1, which is 100 grams per liter. So grams per liter both cancel. It's going to leave you with your volume in liters. So 0.34 liters. That's what V1 is. Now, unlike making up a percent solution, with this, we actually can figure out exactly how much water. So how do I know how much water will I add? If I know I'm going to use 0.34 liters, what's the total volume? 1.7. So what are you going to do? Just subtract. So if you take the final volume minus the volume of the concentrated solution, that'll actually tell you exactly how much water you will add. So 1.7 minus 0.34 is 1.36 liters. That's the water. Because that's going to make up the difference. So with dilutions, you can actually figure out how much water. When you make up a percent solution, when you make up a molar solution, you really don't know how much water. You're just trying to get to a volume of the solution, solute, and solvent combined. It's not terrible. A lot like the gas laws. Just follow it every single time. Do the steps. So here's one more. And this is a new one. This one's not in yours, so just add this. This was the one that I said I made up a new one, and then I realized we hadn't even gotten here yet. So I'll give you a minute. See if you can assign. Use the same formula. Assign the units. Rearrange the formula. Plug it in and solve. So what's the one thing you don't know? C1. Okay, so C1 is what you're trying to solve for. V1 is 275 milliliters. C2 is 5.25%. And V2 is 1.75 liters. So the only issue with this is, can you do this multiplication even? What's the unit issue? Well, percent you can use. You can just give your answer in percent. Okay, so percent's fine, molar would be fine, grams per milliliter would be fine, grams per liter would be fine, any kind of concentration as long as they're the same. But in this, look at your volumes. So you have 275 milliliters and 1.75 liters. That you can't do because you're not going to get them to cancel. So you need to convert one. And it doesn't matter which one, convert the milliliters to liters or the liters to milliliters. So 275 milliliters times 1,000 milliliters on the bottom, 1 liter on the top, 0.275 liters. So you've got to make sure that you put the volume, if 2 volume units you have, they've got to have the same unit value. 2 concentration values you have, they have to have the same unit value. Now I can do it. So what do I got to get all by itself? So then to do that, so if I divide both sides by V1, V1 goes away from the left, and it's in the bottom over on the right. 5.25% times 1.75 liters. You can leave it in percent. It does not have to be molarity or grams per mil. You can leave it in percent. It's super easy that way. Divide it by 0.275 liters. I got 33.40909090991%. To what?
3.
So keep the 3, the 0.4, and the rest of it goes away. Yeah. So 33.4%. Okay, so sort of follow the same as you did with the gas laws. Just sort of set each one up, rearrange the formula, and just plug them in that way. Make sure your units are the same. So the last topic is a theory topic. They go back to theory stuff. So the last topic is about how these solute molecules are moved around within the aqueous environment of the body fluids. So remember, whenever we're talking about aqueous, it's things dissolved in water. So osmosis occurs because of differences in water concentration. So water concentration, the amount of solvent within different regions of the body, if they're not exactly the same, water is always going to try and balance those things out. So they call the cell membrane a semi-permeable membrane. And it's semi-permeable because semi means sort of permeable and sort of not. So it allows some molecules to pass, but not others. So I found this picture. So here's our cell membrane. And so remember this phospholipid, this is the barrier. Because the inside of the phospholipid, this is the nonpolar region. Nonpolar regions are not going to allow polar molecules, water molecules, or salt molecules from freely passing through because those are all watery. So nonpolar, this sort of oily environment is going to be a barrier to things like glucose. So glucose, boink, just bounces off. So it's like a little oil barrier. So polar molecules, like glucose, can't pass. Salt molecules, like sodium ions, they can't pass either. So they're blocked because of this oily layer. In fact, even water molecules that are inside and outside, they cannot freely pass across this layer because it's polar and nonpolar. And you know when oil and water get mixed together, they automatically separate. So you can think about this as being this oily barrier in the center, and it's going to prohibit polar and charged molecules from moving. But we just got done saying that water wants to balance this. So the only way that water can balance it is by passing through a channel. And that's that integral protein. So that one is a good picture. I thought it kind of looks like there's a space. There's like a hole. There's a channel in the very center. If this is a water channel, it will let water molecules move in or move out. And it's always going to be dependent on the concentration. So if you have more water in one area, then those water molecules are going to want to move out to the other side of the membrane to try and balance it. So if I have water, lots of water, not as much salt, some salt, but more water. Out here, not so much. Out here, we have more salt, so we have less water. So in this situation, there is more salt outside the cell, less salt in. So less Na, more Na. All right now. Keeps erasing my words. But if I have more salt, that means there's less water. Okay, so more solute is less solvent. So here, there's less water. Down here, there's more water, comparatively. Well, that channel is not going to let sodium pass. That's a water channel. And water channels are actually always open. So water channels will allow water to go in and out, but they won't allow salt. The salt is like stuck. And so where is water going to go under these conditions? What do we say osmosis does? Things always want to move from high concentration to low. right? So if you've got an imbalance, it always wants to try and bring it into a balance. So if you look at this, which way is the water molecules going to want to go? Where's there more water? Inside of the cell. So water molecules begin to move out. They begin to move out, and that way they're diluting the salt outside. They're trying to balance the amount of water and salt on both sides of the membrane. Does all the water move out? No. It goes from high concentration to low concentration until concentrations are equal, right? So that's always the drive. And water channels allow that to happen. So think over here. So think over on this side. We'll take these ones off. So what if we have the exact same setup? So we have the exact same barrier that's present. So we still have a little water channel. Here's our water channel. But now on this side, instead of having a lot of sodium outside, there's not very much. So we have a few, but we have a lot more sodium inside. So we still have some sodium outside, but comparatively, we have a lot more water. So H2O. Inside, not so much. There's a lot of sodium, so there's less H2O. That channel won't let salt move, but it will let water move. So this is a specific water channel. So now, if you count, there's like 1, 2, 3, 4, 5, 6, 7 molecules of water outside, and inside there's only 3. So there is more water outside, less water inside. More sodium outside, or sorry, less sodium outside, more sodium inside. That's going to cause water to go which direction? So it's going to go down. So you're going to have water molecules go through the water channel and move in. Water molecules moving in. Not all of them, but they're going to, again, they're trying to go from high concentration to low concentration to bringing those concentrations into balance. So these two are showing you the tonicity, showing you how solutes will cause water to move. This one on this side where you have more solutes, this is the hypertonic. Hypertonic, the word hyper is high, like the hyperactive kid is very active. Okay, so I always think of hyper as high, tonic is solute. So this is a high solute solution. And it's always the conditions outside of the cell. It's never what's inside, it's always what's outside compared to what's inside. So in this one, there's more solute outside compared to inside, and this will cause water to move out. The other one, you have more water on the outside, more solute on the inside. So we have more sodium on the inside, less sodium on the outside. They call that hypotonic. So hypo means low. Hyper is high, hypo is low, and tonic is solute. So this has a low solute outside and will cause water to move into the cell. What if you had the exact same amount on both sides? Okay, that is isotonic. Okay, so if the amount of solutes in water on both sides are balanced, then any water moves in will be balanced by water going out. So you may have some still moving through those channels, but if water molecules are going in, the same number are going out, so there's going to be no net change. That is isotonic. This is when you have balanced solutes in and out. And that'll cause no water to move at all. So water moves because of this barrier. Water can move because there's a channel. So water has its own channel, and there is nothing prohibiting water from being able to pass using that channel. It can't pass straight through, but it can by osmosis. The pressure exerted when you have high concentration to low concentration, that is osmotic pressure. So that is the pull of fluids, and it's always from areas where there's less solutes to more solutes. So in a way that most people think about it is they always say that water is always moving towards area of higher salt. So I have, well, maybe it's actually in here. I have a nope, I have to close this to show you. I have a link. Come on. Just doesn't like this. I have to put my mouse on. Then all I have to do is click on it. But it won't let me do it otherwise. Okay. Come on. So this shows.
We want to show you the shortcuts that if you don't even have a clue what knowledge you might have that can make a difference, show you how you can extract that.
Okay, it's actually easier to see this where you are. So I like this, so they're like, can you touch yourself? Ow. So then you put it on a slide, and you add some saline, 0.9% sodium chloride. Remember, that's physiological saline. So that's an isotonic condition. So in this is only magnifying it 40-fold. So when you look at it, you're like, yeah. So then you go up and you magnify it 100-fold. Now you can start to see, can you see like little balls, like little circles? Okay, but still, this is really not close enough. So now we need to go, this is 150. So you go from 150, but I do have this one. So now we're at 400. Okay, so now at 400, can you see the shape of the red blood cells? Can you see how they're round? Look how they look almost like donuts. They're actually thinner in the center than they are on the outside. So they call them a biconcave disc. So there's a couple of other ones. They'll roll through so that you can see them. And you can see them a little bit better and a little bit better as it goes along. That's magnification of 400. This is using a light microscope. Now as you're looking at them, you can start to see as the ones floating, see how the ones that kind of turn, can you see how they're flat looking? Now you can see them, so these are flowing along. But this is in isotonic conditions. So you can make them out really well, that type of shape that they have. It's really optimal for oxygen carrying, and they bounce off each other this way. That's a white blood cell. So if you see any of those in there, those are not just puffy red blood cells. Those are actually white blood cells. They help with immunity, help with protection. That looks like a lymphocyte. It's like the size of a blood cell. There's another one. So this is 1000x. So actually, this is like whale immersion is what you have to use. But you can really make out the shape of the cells floating about. I don't have this. This is actually 1500x magnification. We don't have injectors that have this type of magnification. So no. So they are floating. So now here's what they're going to do. They're going to add 10% sodium chloride to the salt, or to the solution. So this is increasing the solute. This is decreasing the amount of water that is outside of the cells. By increasing your salt, you're decreasing the water. Now, it starts happening to the cells. Yeah, so do you see how they start now almost looking like contacts? Like they're kind of like, they're getting this kind of like deflated, more curved shape. That is because they're losing water. So those hypertonic conditions, when patients get really dehydrated, their cells begin to lose water. Oftentimes that affects brain function, so they're like not really with it. They're all out of it from that dehydration. Now this one, they turn back around and they add distilled water to it. And so you can see right away those cells are starting to look more normal. Then as you watch, do you see the ones they're going to start showing? They'll start showing up. This one you can kind of make out these outlines. They're much bigger compared to the one that is still that big. You see how big and round they look like balls? Because now they don't look like those biconcave discs. In fact, they will pull in with hypotonic. Water outside is really high. Water moves in. You can see them pretty good right there. Water moves in. The cells begin to swell. So instead of being like that biconcave disc shape, now they're like balloons, all swollen up. And that one right there, this is one where you can actually see. Can you see right here? It looks like something's coming out. So they'll actually pop. They'll get as big as they can, and then the cell membrane will explode. So that creates, they call them ghost red blood cells, because you can only make out like this outline of what used to be there because they popped and all the stuff came out, and all that's left is like the empty cell membrane, sort of like a popped balloon that's just left behind. That happens under hypotonic conditions. Hypertonic, water comes out and it shrivels up because there's a lot of salt out. Hypotonic, a lot of water outside, water moves in, and the cells swell up. So that's the difference for them.
Hey, it's Tony Robbins.
Dean Graziosi, what's up?
Listen, we want to ask you, what do you think it's like to be able to have the privilege to take something you know, share it with...
Okay, so I left the link on there. There was one that I thought that was kind of like the simplest looking one. So you can see the same in this one. So you see the same difference. See the normal appearance, that biconcave disc. Then the middle one. Now the middle one is like the last picture. So the middle one is when you put it in a low solute, high solvent concentration, hypotonic, and more water moves in than comes out, and the cells get really big and puffy. And eventually they'll actually lyse. And then the last one, they didn't really catch any good crenated looking cells on that video. If you've done this in lab, like in A&P, I'm sure that you've seen like that. They get all raisiny looking. They get kind of shrunken and deflated in appearance when you put them in hypertonic. So this is why when you give IV solutions, you want to make sure that you're giving solutions that are isotonic. You're giving solutions that are balanced, solutions that are going to keep the cells the same. Even if a patient is dehydrated, you're not going to give them distilled water, because that would cause too much of a tonicity change. Instead, you will just give them volumes of physiological saline just to try and improve the volume to replace what they're missing in terms of fluid, and their kidneys will take care of the excess salt. So that will actually help to keep the cells from changing in terms of their shape and function drastically. So that's what when they talk about physiological solutions, that's always referring to what would be considered isotonic to a patient. So 0.9% sodium chloride, D5W is dextrose 5% in water. That would maintain normal blood sugar, because sugar is a solute. So when you have high, remember we were talking about hyperglycemia? When you have conditions of hyperglycemia, you're really creating a hypertonic environment. You're creating a very high solute concentration in the blood, and you can have cells start to shrink under the influence of that sugar. So diffusion is movement of solute. So diffusion doesn't take place freely unless the molecule can pass through the plasma membrane. So their example is if you take and put a drop of food coloring in water, it'll automatically spread out, right? So it starts off and then spreads. When you pour your creamer in your coffee, okay, you pour it in and you kind of see it go in. And then as it sits, it just automatically spreads out by itself. You don't have to mix it. Mixing just speeds the whole process up. So in this transport, there is what is known as passive diffusion. And passive diffusion is doing just this, going from high concentration of solute to low, which is what osmosis does. But osmosis uses water. For diffusion, simple diffusion to occur, the molecule has to be nonpolar. Because where's it going through? It's going through the membrane. Remember, this membrane's nonpolar. So if it's polar, it's going to get bounced right off. It can only pass through if it's nonpolar. And there's two things that have this ability. What are the two things that diffuse freely? Across membranes, across from the air to the blood. Oxygen and what's the other one? When you take a breath, oxygen diffuses into the blood and carbon dioxide diffuses out. So they have the ability to diffuse because they're gases and they're also nonpolar. So that the barrier of the cell membrane isn't an issue for them. They dissolve into the blood and they get carried along. Glucose, when insulin is there, glucose can get taken into the cell, but glucose is polar. So glucose has to do facilitated diffusion. So it actually has its own channel, like water, but it's a separate channel, and the only time that channel opens is if what is there? Insulin. You have to have insulin. As soon as insulin comes along and it binds to this, then this will open. If you don't have insulin, closed. Okay? It's not going to open. Insulin is the trigger, binds to a receptor. That receptor tells that channel to open and lets glucose go from the blood into the cells. But notice it's also going high to low concentration. Where there's a lot of glucose, it moves in to where there's less. Okay? So those are two forms, common forms of diffusion. We will mention the last one at the very end, because the last one is going which way? But look at the amounts. So high concentration to low concentration, that's what oxygen, carbon dioxide do. Glucose, high concentration to low concentration. What about that last one? It looks like it's going from where there's not very much to where there's a lot. So that's like the reverse. That's what active transport is, and it's going the opposite direction. So we talked about passive, small molecules, facilitated. But a good application of osmosis and diffusion is dialysis. Dialysis is really the movement of molecules from high to low concentration. So we did this in lab, okay? So in lab, we had this tubing that had teeny tiny microscopic holes in it. And inside, we had some really big molecules. And we had some small molecules. And we had some sort of medium-sized molecules. And that's inside of that tubing. Let me make sure this tubing looks like it's actually tubing. It's just have little tiny holes in them. Took that tubing and we knotted it off and we put it in distilled water. Okay? So outside of this tubing, we have lots of solutes. Outside of the tubing, we didn't have any. And so after an hour, what did we do? We tested for what? There were three things. We tested for glucose, we tested for starch, and we tested for the littlest one. What was the littlest solute? Salt. So we tested for salt, for glucose, and for starch. Those inside of the tubing, that's high concentration. If they were small enough, what did they do? Yeah, they could diffuse. So they could move. So these little itty bitty molecules, like the little teeny tiny red ones, they diffused out. That's the salt. Diffuse from high concentration to low concentration. Did they all come out? No. Again, it would go until it's isotonic. So the salt would go from high to low until you had salt balanced with the salt inside. How about the glucose? If the glucose was small enough, I did that one in purple. So the little one, the medium, if it could move, it would. It would always move from high concentration to low concentration until it reaches a balance. But now those big molecules, the starch molecules. The starch molecules, did they pass through? No. They can't diffuse. They were too big. It's not that they didn't want to. They can't diffuse because of their size. This is how your kidney works. So your kidney does this on a constant basis. It does dialysis as a means of being able to filter out by diffusion and osmosis, removing excess wastes and molecules that you don't want. So if a person whose kidneys are failing, they can undergo an artificial dialysis. They call it hemodialysis. So first, just a little bit, we've got enough time, a little bit about your kidney. So how many kidneys do you have? Two. Okay, and they lay right about here, so like kind of middle of the back. They're about 4 inches long. And inside, they have microscopic filters called nephrons. One kidney has 1 million nephrons. So there's 1 million microscopic filters. These are nephrons. You need at least 250,000 of these to be working. So you're really born with 4 times more filters than you need. If you have less than that, then they start talking about kidney failure. Okay? This is why people can donate a kidney, because you got 2 million and you only need half of one, really. So you only need half of one functioning in order to be able to survive. When you start dropping below that, then you're in renal insufficiency. It just means that your kidneys can't filter it out fast enough. And so then you start to see waste products build up. So in your blood, I talked a bit about your blood. So your blood has that suspension. So what are the big pieces? What are the really big particles? There's 3 types. Red blood cells, white blood cells, and platelets. These are kind of like the starch in the dialysis tubing. They can't get out of the blood vessel. They're too big, so even in the filtering, they never leave the blood. If they do, then your filters are damaged. Okay? So if you find red blood cells in the blood, that means that your filters have been compromised and some blood is leaking out of the kidney, and it shouldn't. So under normal conditions, this is not filtered out. Remember, we also talked about proteins. So those make the colloid of the blood. So proteins in your blood, they're in plasma. They make the blood kind of thick, kind of like an egg white kind of consistency. Those are too big. So they're not filtered out. So when the red blood cells, white blood cells, platelets, and proteins, as they pass through the filters of the kidney, they stay in the blood vessel. They never come out. But all those other solutes, so all the other solutes like salts, nutrients, wastes. Those are small enough, so like our dialysis tubing, they're like the salt. They're small enough that they actually get pushed out of the blood, filtered out, and then your body actually reabsorbs what it wants. So the nephron not only filters everything out, but it pulls most of the salt back in, it pulls all the nutrients back in. The only thing out of there it doesn't want is what? The waste part. So much of the salts and nutrients get reabsorbed. They're really reclaimed. And this still happens in the nephron. So the blood gets this back. Water is another one. So not just solutes, but the solvent as well. So water gets filtered. Depending on your hydration level, you may excrete a lot of water. Like if you're like doing your drinking of water, okay? So if you're getting normal amounts, then you're going to have more water excreted. If you're not, and you're in this minor state of dehydration, then you may have less water excreted. That can adjust depending on your hydration levels. This happens, you filter your blood about 36 times a day. Your entire blood supply, so about a cup of blood gets filtered through your kidneys about every minute. It's really about a half a cup, about every minute. So that correlates when you think about 5 liters of blood every day, 35, so it's really 33, 30, it depends on the person, 30 to 35 times per day, your entire blood supply is filtered. So you go out and you have the salty meal. So you go get the fried chicken with the French fries and then the corn sticks that you like dip in salt. Yeah. Okay, so you go and you have that. So there's this massive influx of sodium. And you're like, whew, I'm really thirsty. And then your hands start getting all puffy and you get some minor edema and everything else. Your ankles are swelling. I'm like, oh, that was bad. Shouldn't have done that. Okay, your kidneys can handle that. Okay, over the course of about 18 hours, your kidneys will just keep on flushing that excess sodium. You may feel yourself more thirsty because you're trying to balance that excess solute, because it's really creating a hypertonic blood. So you're like, oh, I'm really thirsty. So you're drinking more water. That's also going to promote the filtering. That's going to promote more water and salt loss to try and bring it back. So for most people, if you eat really salty, it comes back. Because it's 35 times a day, the entire blood supply gets cleansed. So think about somebody that has less than 250,000 nephrons. So instead of having 2 million, instead of having 1 million, instead of having 500,000, they're falling into that low percentage. Now, what starts happening to these? This is where this last slide shows. And this is why they have to go in for hemodialysis. So in the blood, they may have salt values like sodium, potassium, calcium, carbonate. They're not balanced. It's because nutrients come in and fluids don't go out. Any salts that come in build. Salts that get transferred into cells may end up lowered in the blood and you may not have enough. So the dialysis fluid, much like our tubing, so blood flows through that tubing, red blood cells, white blood cells, platelets, and proteins don't come out. But anything that's high concentration will diffuse out into the dialysis solution. The dialysis solution really has like the perfect solute and solvent concentration. This is optimal solute and solvent. So it is the right amount of water, the right amount of salt. So what do you think in my example? So this is your patient. They come in, they get hooked up. The blood is removed through one port and it's passed through the dialysis machine. In the dialysis machine, it has that dialysis tubing just like we used. So in the dialysis machine, diffusion and osmosis can happen. So what is going to come out of the blood and go into the fluid when you look at this list? What about sodium? Okay, so it will go from high concentration to low concentration. So sodium, in my example, sodium is higher in the patient, so it will diffuse out of the patient and into the fluid. What about potassium? Okay, so potassium is going to move out of the blood and into the fluid. Now that fluid is constantly recirculated and constantly removed, and fresh fluid is added in. So that means the fluid always stays pretty consistent. So even though sodium's moving out, they're draining it away. So that fluid helps to keep that balance. What about calcium? There's actually a little movement backwards, because optimal would be 1.25 milliequivalents. And so if you're only at 1.2, a little calcium will move into the blood. What about bicarb? It'll diffuse into the blood, all going from wherever it's at high. It doesn't matter if it's a high concentration in the blood or high concentration in the dialysis fluid. It is going to move from high to low until those concentrations are balanced. And in fact, it keeps moving until the concentrations are more like the dialysis fluid. What about magnesium? It's going to move out. It's going to go from 1.5 milliequivalents to 0.5. Chloride. A little bit will move in. What about glucose? So if it's 4.5, it'll go. So it's going to go from the dialysis fluid and into the blood. So you see the arrows. It doesn't mean everything doesn't come out. Everything doesn't go in. It does it from high concentration to low concentration until it reaches that iso point, until it reaches a balance point. So at the end of dialysis, the patient's blood. Oh, and there's one other I didn't put in. Wastes. The most common wastes are urea, uric acid, and creatinine. And there's none of this in the dialysis fluid. So what happens? It just keeps going. So the urea, the uric acid, the creatinine, they just keep dialyzing, keep diffusing from high concentration to low concentration. You keep circulating and putting in fresh dialysis fluid. So by the time the patient's blood has gone through this a couple of times, what's the condition of their blood? Their blood is almost just like the dialysis fluid. So it never really gets a chance to become equal until it is equal to what the concentration of the optimal solute and solvent is. So some patients will actually lose a couple of pounds because of water loss. So water will get pulled off. Some patients may actually gain weight because they were actually in a state of dehydration and they've actually had water increased. So water will osmose from high concentration to low concentration as well as these are balancing. How long does this take? About 4 hours, okay? And so how many times for a patient that's in renal failure, which means less than 10% functioning, if you're in renal failure, less than 10%, how many times a week do you have to do this?
It's about 5.
3 is the typical. So 3 you go Monday, Wednesday, Friday, or you go Tuesday, Thursday, Saturday. And so you spend like that entire morning or the entire afternoon doing this. So when you wake up the morning that you go to dialysis, your blood is all out of whack. And so how do you feel? Terrible, okay? Yeah, you're really lethargic, tired. You almost feel nauseous oftentimes, and it's because of all of these solute imbalances. Then you go to dialysis, and in 4 hours, you go from this to this. So how do you feel after that? Most people, what do they want to do? They want to go home and go to sleep. Okay, so that's what most people, like dialysis, you wake up, feel crappy, you go get dialysis, now you're exhausted, and then you go home, go to bed. The next day, that's when you go grocery shopping, that's when you actually go to doctor's appointments, because your blood is not here yet, it's just kind of here. And throughout the day, it's just going to get a little worse. And so that's like half of your life is this. Every other day is this. So it's like, that's just horrible. Like that's, and there are people that do this for like years, decades, 30 years they've been doing dialysis. And most of the time, this is either because you were either born with non-functional kidneys, you had some really terrible kidney infections as a child and you have so much scarring and damage, you've had some kind of infection that ended up causing damage to kidneys along the way. But another big issue, and really more than half of the patients that you take care of that have to do dialysis, why? Type 2 diabetes, because of the damage that hyperglycemia has caused to those filters. When the blood gets super thick with sugar, it blows the filters out and they don't grow back. And so that's this. So that's this 50% of the time. But at least you can do it this way. They're actually working on like a little computer chip filter. So it is a filter that will like monitor the solutes as it comes out of the patient's blood. And that way you can actually, it'll be able to do this like constantly. Monitor, filter, and then pull solutes out to try and keep waste levels from building up.
That won't be cheap.
No, but for somebody that's like spends half of their life going to the dialysis center or recovering from dialysis, it would really allow you for more manageable time. Okay? All right, I'll stop there. It's the end. The end of chapter 8. Okay? So I do have, really. Did I not pick them up? Well, I swear. I picked them up. Oh, here they were. What? I knew I picked them up. I have your... Do I have them? Yes, they're right here. They're just tucked under everything. Okay, so this is your take-home test. You have a week to do it. Okay, you can read the rules. You can utilize any resources, but not me. Okay, there's no time limit. So I don't care if you work on it for 10 hours, you should not have to. Okay, you can use any resource. I mean, I think that it's kind of ridiculous for me to say, like, you can't talk to each other about it because that's just ridiculous. That's not going to happen. So I don't care if you work on it together, okay? But I will ask you to not give anybody answers that were not active participants in the working of the problems. Because if you do that, you're really not helping that person, okay?
Do we bring you the non-perishable?
Yeah, so there's two things. One, I did change the date, so it is due next Wednesday. Okay, so you'll turn it in next Wednesday. The MyLabs Plus assignments will close next Wednesdays for chapters 7 and 8. Okay, so as you go through and start looking at these, you should see that these questions like follow directly along material that we've covered. I do have the lecture videos posted. I do have the marked up PowerPoints posted as well. So those are all options like and things that you can resource and look at in Moodle. So this will be an exam 4 module is where you would find it. Extra 5 points if you will bring $5 worth of non-perishable food items because this is Thanksgiving. And so Nash does actually have a food pantry. So Nash on the regular provides for non-perishable foods for students. Okay, so it's not like going out of campus and going someplace and you don't know. This is actually, there are students that are really struggling and may have a difficult time. So you just, I don't care what it is, okay? So non-perishable, it can be like stuffing mix. It could be like boxed mashed potatoes. Okay. It could be green beans. It could be, canned goods. It could be soup. Anything like that. Something that they don't have to refrigerate, that they don't have to worry about. Okay. Don't be bringing too much super sweet stuff. I'll be judging you. Okay. But that you can do as an option